गुड मॉर्निंग मैम।
गुड मॉर्निंग। एलिया बात कर रहे हैं।
यस मैम।
एलिया बात कर रहे हैं।
यस मैम।
क्या हाल है?
ठीक मैम। मैम हाउ आर यू?
फाइन, थैंक यू। हेलो हलीमा।
Assalamu alaikum, ma'am.
हाउ आर यू?
I'm fine, ma'am. How are you?
आई एम फाइन, थैंक यू। हेलो आमना। आमना का माइक नहीं काम कर रहा। आमना माहम। हेलो आमना।
Yes, ma'am. Assalamualaikum.
वालेकुम सलाम। हाउ आर यू?
Alhamdulillah, ma'am. I'm good.
गुड, ग्रेट। ओके,
How are you?
आई एम फाइन, थैंक यू। हेलो महनूर।
Assalamu alaikum, ma'am.
वालेकुम सलाम। हाउ आर यू?
I'm good, ma'am. How are you?
आई एम फाइन, थैंक यू। Okay, right. So let's wait for 1 minute and then we start, okay? Okay, so let's take the attendance, okay? It's the 5th of May. Okay, so Ahmad Asan is absent. Fahad bin Ahmad is absent. Aisha is absent. Ali Musa is absent. Mahnoor,
Yes, ma'am.
yes, good. Nimra, okay. Sayyid Azad Asad, Farooq Ahmed, Awais Khabargil, Laiba Khalid, Tahib Khan,
Present, ma'am.
Elia,
Present, ma'am.
good. Amna,
Present, ma'am.
good. Nashra, Aruba, Halima,
Present, ma'am. Nashra.
Nashra, acha. Halima,
Present, ma'am.
Wab, Sumavi, and Saul Rafakat. Okay,
Present, ma'am.
good. Okay, what were we studying last time? क्या पढ़ रहे थे हम?
Cosmos.
Cosmos, yes. We were talking about the cosmos. Let me share the board. So we were talking about the cosmos. What is the cosmos? Yes? What is the cosmos?
Cosmos is the world around us, including all the galaxies, the matter, and so on.
Can you please repeat it?
Cosmos is the world around us, including all the galaxies, the stars, the black matter, and so on.
इसको world नहीं कहते, इसको universe कहते हैं. There's a difference, right?
Sorry, ma'am?
इसको universe कहते हैं, world नहीं कहते हैं.
Yeah, exactly.
हाँ, there's a difference. Universe में ये सब कुछ आता है, ठीक है? So we talked about galaxies, हाँ जी, we talked about stars. You know that the sun is a star, है ना? Yes. और क्या बात की थी हमने? So we are talking about chapter number 5, right? So this is cosmology, right? This is astronomy. This is a very interesting branch of physics, and in fact you don't need to be a physicist actually to be familiar with these things. In fact, children are very interested, teenagers are interested, because there's a lot of sci-fi movies about this, and they're made in a way that you can understand them even if you have not studied physics, right? There are a lot of videos, a lot of documentaries, and they're based on very important and very interesting concepts about the universe that we live in. We also talked about the Big Bang. We talked about the Doppler effect, the Doppler shift, the red shift and blue shift, right? This was, we talked about a very important equation which is equal to mc squared. In fact, this is one of the most important equations in physics, and it's a very simple equation, but it's a very powerful equation, right? It relates energy to mass, and this is the speed of light. We know that the speed of light is the highest speed that's possible, which is 3 into 10 raised to 8 meter per second, right? And then the square of this will be a huge number, right? And you know that this is a very powerful equation because it shows us that matter can be converted into energy and vice versa. And this equation is the basis of the fission process, which gives us nuclear power. You know, we have power plants in Pakistan as well. And it also gives us the concept of fusion, which is a very powerful concept of energy generation. This is under experimental prototype. Prototypes are being worked on at the moment. It's not at a stage that can be commercialized, but if we are able to succeed, we will have more energy than we need. And this is the mechanism by which energy is produced by the sun. So, this is again, the sun is a huge source of energy. Life on Earth would not have been possible if we did not have this, right? So, fission and fusion are opposite concepts. In fission, you have one nucleus, like a uranium nucleus, which breaks into two nuclei, and this emits neutrons and radiation and a lot of energy. So there's a small mass difference that can be multiplied by the light velocity squared, and you get a huge amount of energy. The energy that we measure in this case, normally the units of energy we talked about in chapter 1 were joules. But now in nuclear physics, normally the units that we use for energy are electron volts. And since the energy is very large that we're talking about, therefore we talk about mega electron volts. Okay? Okay? So
Yes,
again,
ma'am.
okay, and fusion is the opposite process. Fission is the process in which this can be uranium, a heavy nucleus, right? Which is a fissile nucleus, okay? At the concept of radioactivity, okay? So fusion, in this case, two small nuclei, like let's say hydrogen plus hydrogen, can fuse together to give us another bigger nucleus like helium. And in this case, again, there will be a mass difference that can be multiplied by the square of the velocity of light, and you will again get a huge amount of energy. We will also solve some examples and problems, and you will see how this works. So these were some of these important concepts that we talked about. Now I'm going to share a video with you, okay? So, so can you see this video?
Yes, ma'am.
Okay, so I'm going to play it for you, okay?
The universe began its cosmic life in a big bang nearly 14 billion years ago, and it's been expanding ever since. But what is it expanding into? That's a complicated question. Here's why. Einstein's equations of general relativity describe space and time as a kind of interconnected fabric for the universe. This means that what we know of as space and time exists only as part of it and not beyond it. Now, when everyday objects expand, they move out into more space. But if there is no such thing as space to expand into, what does expanding even mean? In 1929, Edwin Hubble's astronomy observations gave us a definitive answer. His survey of the night sky found all faraway galaxies recede or move away from the Earth. Moreover, the further the galaxy, the faster it recedes. How can we interpret this? Consider a loaf of raisin bread rising in the oven. The batter rises by the same amount between each and every raisin. If we think of raisin as a stand-in for galaxies and batter as the space between them, we can imagine that the stretching or expansion of intergalactic space will make the galaxies recede from each other. And for any galaxy, its faraway neighbors will recede a larger distance than the nearby ones in the same amount of time. Sure enough, the equations of general relativity predict a cosmic tug-of-war between gravity and expansion. It's only in the dark void between galaxies where expansion wins out and space stretches. So there's our answer. The universe is expanding onto itself. cosmologists are pushing the limits of mathematical models to speculate on what, if anything, exists beyond our space-time. These aren't wild guesses, but hypotheses that tackle kinks in the scientific theory of the Big Bang. The Big Bang predicts matter to be distributed evenly across the universe as a sparse gas. But then, how did galaxies and stars come to be? The inflationary model describes a brief era of incredibly rapid expansion that relates quantum fluctuations in the energy of the early universe to the formation of clumps of gas that eventually led to galaxies. If we accept this paradigm, it may also imply our universe represents one region in a greater cosmic reality that undergoes endless, eternal inflation. We know nothing of this speculative inflating reality, save for the mathematical prediction that its endless expansion may be driven by an unstable quantum energy state. In many local regions, however, the energy may settle by random chance into a stable state, stopping inflation and forming bubble universes. Each bubble universe, ours being one of them, would be described by its own Big Bang and laws of physics. Our universe would be part of a greater multiverse in which the fantastic rate of eternal inflation makes it impossible for us to encounter a neighbor universe. The Big Bang also predicts that in that early hot universe, our fundamental forces may unify into one super force. Mathematical string theory suggests descriptions of this unification, in addition to a fundamental structure for subatomic quarks and electrons. In these proposed models, vibrating strings are the building blocks of the universe. Competing models for strings have now been consolidated into a unified description and suggest these structures may interact with massive, higher dimensional surfaces called branes. Our universe may be contained within one such brane, floating in an unknown higher dimensional place, playfully named the bulk or hyperspace. Other branes containing other types of universes may coexist in hyperspace, and neighboring branes may even share certain fundamental forces like gravity. Both eternal inflation and branes describe a multiverse. But while universes in eternal inflation are isolated, brane universes could bump into each other. An echo of such a collision may appear in the cosmic microwave background, a soup of radiation throughout our universe that's a relic from the early Big Bang era. So far, though, we found no such cosmic echo. Some suspect these differing multiverse hypotheses may eventually coalesce into a common description, or be replaced by something else. As it stands now, they're speculative explorations of mathematical models. While these models are inspired and guided by many scientific experiments, there are very few objective experiments to directly test them yet. Until the next Edwin Hubble comes along, scientists will likely be left to argue about the elegance of their competing models and continue to dream about what, if anything, lies beyond our universe. One of our favorite things about the TED-Ed community is our shared passion for big, sometimes unanswerable questions. Students in our TED-Ed Cubs program, for example, are using the TED platform to explore big questions that began its cosmic life in a big... The universe began its cosmic life in a big bang.
Okay, so what was this video about? This video was about yes. Video was about
Ma'am, it was about the universe and its expansion and formation.
आमना बोल रही है कौन बोल रहा है अपना नाम भी
Ma'am, Amna ma'am.
आमना महा yes it was about the expansion of the universe और ठीक है very good मैंने last time भी आपको बताया था कि in fact the expansion of universe पहले ये लोग इसको इसके बारे में बात करते थे लेकिन recently इसका नोबेल प्राइज भी दिया गया था मेरे ख्याल 2019 में कि हाँ 2019 में तो आपको मैंने उसका लिंक भी अपलोड किया है Moodle में आप उसमें पढ़ सकते हैं ठीक है कि the universe is expanding ठीक है ना yes महा आमना महा आप और क्या कह रही थी
मैम आपकी आवाज़ बहुत स्लो है ना समझ आने के बराबर
okay Okay, so I told you that I've uploaded the link for the Nobel Prize in which the expansion of the universe has now been proven. This was a concept that people were working on before, and it was predicted. Now it has been proven, and a Nobel Prize has been awarded for this. ठीक है जी, और इस वीडियो में क्या था?
मैम कुछ फॉर्मूलाज वगैरह आए थे वीडियो में जहाँ पे कैलकुलेशंस वगैरह की थी साइंटिस्ट ने कि ये कैसे एक्सपैंड करती है और ये सारी चीजें, ये स्टार्स कैसे आपस में टकराते हैं, कम्युनिकेशन कैसे होती है, थोड़ा सा इसके ऊपर था।
ठीक है, अब ये फॉर्मूलाज आपके लिए नहीं है, ठीक है, दीज आर नॉट इंक्लूडेड इन योर चैप्टर, ठीक है, लेकिन आपको मेन कॉन्सेप्ट की समझ होनी चाहिए, ठीक है। So anything else anyone would like to add? Video start with the Big Bang. Now Big Bang again is a model, is a theory about how the universe began, ठीक है ना, ये came into existence, and इसके क्या proofs हैं और इसके क्या evidences हैं. There are many theories and this is one of them. This is one of the most accepted theories, ठीक है, इसकी भी हमने बात की थी last class में, right? और इसके अलावा it talks about the concept of fundamental force, right? हमारे पास कितनी fundamental forces हैं, ये आपके चैप्टर में है टॉपिक, and gravity is one of those fundamental forces, right? So इसके बारे में थी ये वीडियो, and you can see for example हमारी बुक में वो कहाँ पे है fundamental forces वाला टॉपिक. Let's look at that. आपसे बात की थी कि फंडामेंटल फोर्स जो ग्रेविटी है उस पे न्यूटन ने बहुत काम किया था ना, वी रिमेंबर दिस, ठीक है. तो ही शोड अस दैट दिस फोर्स इज इनवर्सली प्रोपोर्शनल टू स्क्वायर ऑफ द डिस्टेंस बिटवीन द टू बॉडीज. सो every body is attracted to every other body, ठीक है. So now I'm going to share the book chapter, ठीक है. यहाँ पे you can see now you can see the book chapter, right? So in this case you can see that this is about the 4 fundamental interactions between particles that we have in the universe, right? And so we have theories that explain the fields due to the interaction. This is the diagram that shows you these fundamental forces. You have the strong force, you have the weak force, you have the electromagnetic force, right? And of course you have the gravitational force, and the strong force is the strongest force, and then you can see how it relates according to the scale on this graph. So here you have an explanation for this. You have electromagnetic, gravity, weak and strong forces, and these are created by exchange particles, right? So here you have the electromagnetic forces associated with photons acting as the exchange particles. The gravitational force is carried by gravitons, and this is something that is being worked on. The strong force binds nuclear particles together, protons and neutrons, is carried by gluons. So protons and neutrons are known to be composed of smaller particles called quarks. And the weak nuclear force that causes subatomic particles to change from one form to another. So this happens in nuclear decay, for example. So this is a very important and fundamental concept, and here you have another figure that explains these 4 forces: the strong nuclear force, the electromagnetic force, the weak nuclear force, and the gravitational force. Now we are going to watch a video about this, okay? So let's look at that. Now you can see the video, okay?
If you were to take any everyday object, say a coffee cup, and break it in half, then in half again, and keep carrying on, where would you end up? Could you keep on going forever? Or would you find a set of indivisible building blocks out of which everything is made? Physicists have found the latter, that matter is made of fundamental particles, the smallest things in the universe. Particles interact with each other according to a theory called the Standard Model. The Standard Model is a remarkably elegant encapsulation of the strange quantum world of indivisible, infinitely small particles. It also covers the forces that govern how particles move, interact, and bind together to give shape to the world around us. So how does it work? Zooming in on the fragments of the cup, we see molecules made of atoms bound up together. A molecule is the smallest unit of any chemical compound. An atom is the smallest unit of any element in the periodic table. But the atom is not the smallest unit of matter. Experiments found that each atom has a tiny, dense nucleus surrounded by a cloud of even tinier electrons. The electron is, as far as we know, one of the fundamental, indivisible building blocks of the universe. It was the first Standard Model particle ever discovered. Electrons are bound to an atom's nucleus by electromagnetism. They attract each other by exchanging particles called photons, which are quanta of light that carry the electromagnetic force, one of the fundamental forces of the Standard Model. The nucleus has more secrets to reveal, as it contains protons and neutrons. Though once thought to be fundamental particles on their own, in 1968, physicists found that protons and neutrons are actually made of quarks, which are indivisible. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up. The nucleus is held together by the strong force, another fundamental force of the Standard Model. Just as photons carry the electromagnetic force, particles called gluons carry the strong force. Electrons, together with up and down quarks, seem to be all we need to build atoms and therefore describe normal matter. However, high-energy experiments reveal that there are actually 6 quarks: down and up, strange and charm, and bottom and top. And they come in a wide range of masses. The same was found for electrons, which have heavier siblings called the muon and the tau. Why are there 3 and only 3 different versions of each of these particles? This remains a mystery. These heavy particles are only produced for very brief moments in high-energy collisions and are not seen in everyday life. This is because they decay very quickly into the lighter particles. Such decays involve the exchange of force-carrying particles called the W and Z, which, unlike the photon, have mass. They carry the weak force, the final force of the Standard Model. This same force allows protons and neutrons to transform into each other, a vital part of the fusion interactions that drive the sun. To observe the W and Z directly, we needed the high-energy collisions provided by particle accelerators. There's another kind of Standard Model particle called neutrinos. These only interact with other particles through the weak force. Trillions of neutrinos, many generated by the sun, fly through us every second. Measurements of weak interactions found that there are different kinds of neutrinos associated with the electron, muon, and tau. All these particles also have antimatter versions, which have the opposite charge but are otherwise identical. Matter and antimatter particles are produced in pairs in high-energy collisions, and they annihilate each other when they meet. The final particle of the Standard Model is the Higgs boson, a quantum ripple in the background energy field of the universe. Interacting with this field is how all the fundamental matter particles acquire mass, according to the Standard Model. The ATLAS experiment on the Large Hadron Collider is studying the Standard Model in depth. By taking precise measurements of the particles and forces that make up the universe, ATLAS physicists can look for answers to mysteries not explained by the Standard Model. For example, how does gravity fit in? What is the real relationship between force carriers and matter particles? How can we describe dark matter, which makes up most of the mass in the universe, but remains unaccounted for? While the Standard Model provides a beautiful explanation for the world around us, there is still a universe's worth of mysteries left to explore. Ready to start exploring? Dive right back into the perplexities of the universe with these 2 lessons.
Okay, so this was interesting, right? So these are based on the concepts that you again studied in your chapter. So please study this. Don't be afraid of the number of pages. It's not the number of pages that matters. It's the concepts that matter. And the concepts are simple and they're very interesting. You have a lot of videos about them and you have a lot of information about them. I've also uploaded information, but always start studying with your textbook, okay? Because that's the basic material that we have for the course, and then we supplement it with other materials. I have uploaded some material on Moodle, and I've also shared some with you now in this class as well. So this, what was this video about?
Ma'am, ma'am, it was about electrons and neutrons and the particles. Everything this universe is made up of that. The video started it like the smallest particle is atom, and atom is made up of electrons, and electrons are made up they are made up of electrons, protons, and neutrons, and it was all about their forces of attractions and all about the relation, that how they relate and like attract each other and how they repel each other, and this is all.
Yeah, so it was about the four fundamental forces that we just talked about, right? The strong force, the weak force, the electromagnetic force, and the gravitation force. And it was about fundamental particles, and this concept has been given in the standard model. The standard model describes the fundamental particles that we have in the universe. Okay, so all of these are not fundamental particles. Some of them contain further particles. For example, a neutron contains 3 quarks. So the quark is a fundamental particle, and electron is a fundamental particle. So these are important concepts. Again, they are in your book. You can see them from there. So now I would also like.
मैम प्लीज अपना माइक थोड़ा सा पास कर लें, आवाज बहुत थोड़ी आ रही है.
आवाज और ऊंची करने की करती हूँ.
मैम ये वीडियोस शेयर कर देना मूडल पे.
ये वीडियोस हाँ ठीक है, रिकॉर्ड भी हो रही है ना इसके साथ.
थैंक यू.
राइट, दे आर ओपनली अवेलेबल. आप ये देख सकते हैं जब भी चाहें. मैंने भी इसको ये वीडियोस इंटरनेट से ही ली है ना, टेड टॉक्स बेसिकली. अच्छा, और क्या बात कर रहे थे? आई वांट टू शेयर द असेसमेंट प्लान विद यू. Right. So I'm going to share with you okay, so now this is the assessment plan. You can see it. ठीक है ना, नजर आ रहा है ना आपको? Okay, so here you can see that we have finished assignment 1, we've done a quiz 1, we've done the midterm, and we've done the assignment 2. Now you have to prepare for quiz 2, which is on the 17th of May. This is chapter 3 plus chapter 4. Your lab material is regularly being uploaded. Please prepare the lab material. Okay, so lab exam, I will explain the format of the lab exam to you. The date of the lab exam is 17th June. I will give you a question related to the experiments that we are doing, and I will ask you to use one of the virtual links to perform that experiment. Okay, so you will prepare a report about that lab experiment that has been given to you. That will be a Word document. You will upload it on Moodle before the deadline that's given to you. Please start working on it before I will give you the questions soon. And plus you will make a small video of the experiment that you perform virtually on the links that on one of the links that is that you will be using in this experiments and videos and lab materials, right? So you yourself will decide which link is suitable for that particular experiment. So that video will also be uploaded to Moodle. I will open the link for that. Please compress the video before you upload it, because it will be easier to upload a compressed video. It will be a small video just like the one that I'm uploading. Okay. So this is this will be your lab exam, and of course you have to do this before the deadline. And remember that remember to look at the apps that are suitable for you to record the video and to compress the video. Again, this will be a small video of a few minutes, so it's not going to be a very difficult or heavy or large video. But please look at the apps that you will use. Practice making, performing experiments on those virtual links, making a video and compressing it and uploading it to Moodle to see how it works. The Word document, of course, I will ask you questions related to that experiment. Whatever experiment is awarded to you, everyone will be given a different experiment and they will prepare a Word document about that. So this is going to be your lab exam. And the final exam will be on the pattern of the midterm exam. This will be chapters 3, 4, and 5. Okay. So again, in this case, you will show the working on a document and you will upload that document. You will do the MCQs in Moodle like you always do. Plus, you will also switch on Zoom with the camera. Is that clear? Okay.
Yes, ma'am.
Yes मैम एंड मैम इट इज रिक्वेस्ट अगर आप नेक्स्ट क्लास में दोबारा थोड़ा सा लैब एग्जाम को भी डिफाइन कर दें और कोई एक लैब एक प्रैक्टिकल क्लास में लाइव करा दें कोई एक थोड़ा सा ताकि हमें एक आइडिया हो जाए कि मैम हम कर तो रहे हैं लेकिन फिर भी एक बार आपके सामने करेंगे तो क्या पता हम मिस्टेक्स कर रहे हो वो क्लियर हो जाएंगी हमारी।
मटेरियल देखा जो मैंने अपलोड की है, अभी मैंने काफी सारी वीडियोस अपलोड की, सब हमने बनाई है लैब के डेमोन्स्ट्रेशन के लिए। आप इनको चेक
मैम
ठीक है। Check the material that has been uploaded and practice this material. Okay.
ओके मैम।
मैंने इस वीक में और लास्ट वीक में काफी सारा मटेरियल अपलोड किया, उसमें बहुत सी डेमोन्स्ट्रेशन वीडियोस की हैं, तो वो उनको आप देखें और उसी के मुताबिक आपने बनानी है। ठीक है।
ओके मैम।
और आपको जो क्वेश्चन आएगा वो जो हमने बनाया उससे थोड़ा डिफरेंट आएगा, ठीक है, लेकिन वो उसी से मिलता जुलता उसी कॉन्सेप्ट के बारे में होगा जो कि हमने पढ़े हैं। ठीक है।
Yes, ma'am.
Okay, so now we are going, the meeting is going to end. So this is your homework. Please look at these points that we have discussed. Prepare for your quiz 2, prepare for the lab exam that's coming up. And we also have to decide the date of the final exam, okay? So the last week of June, we have decided, I will decide the particular day of June that will be suitable for this. ठीक है ना? Maybe the 28th of June should be okay. It's a Friday. ठीक है ना?
Yes, ma'am.
Okay, ma'am.
So we can fix 28th of June and then you can 28th. Okay? During the class time. But this will be a 2-hour exam.